well, I'll try and do this for each of these kind of groups of scientists. Millikan and Fletcher are important names to tie to each other. We should tie, they did the oil drop experiment. And we should tie that they came up with the relative charge on an electron, or sorry, the exact charge on an electron. I don't care what the exact charge is, I just want to know that that's what they did. Does that make sense? Okay. Before that?
The Thomson model of the atom.
So we have got the Thomson model of the atom, so arguably we've got Thomson as a scientist name tied to the plum pudding model. Thomson's also tied to the discovery of the electron, thereby also suggesting the discovery of a proton. Right? So the electron becomes really important for Thomson. Plum pudding model is tied to him, but why would we put less emphasis on the plum pudding model?
It's incorrect.
It's incorrect, which we'll see here in a second. Make sense? Okay. So, my story used to be that Rutherford and Thomson didn't like each other, and so Rutherford set out to prove Thomson wrong. As a lot of you already discovered when doing research about these scientists, that's not true. Right? Entirely false statement. Okay? So that takes away some of my fun narrative. Right? But we could switch the narrative around and say that Rutherford was actually just a really good scientist because of the design of this experiment. Because he could have designed this experiment to get a different conclusion that would have supported Thomson, but also would have been entirely false. Okay, so here's the design of the experiment. We're running under, that's what an atom looks like, plum pudding model. Okay, so sea of positive charge, and these electrons floating through the middle of it. Okay? Because that's our model, if I fire a positively charged particle at this thing, which we'll talk about here in a second as well, that positively charged particle should just pass straight through, because there's nothing really to block it. Okay, we don't have a mass on any of these particles yet. We just know that they exist. So that means if I fire a positively charged particle at this atom, it should immediately pass through. Okay, and so that's what this model is trying to show. Okay, or what that drawing is trying to show up top. Does that make sense? So now the question is, how do we design an experiment to do this? So number one, we need these positively charged particles. Alpha particles are a form of radiation. You don't need to stress a whole lot about that for the sake of this class, but they are particles with mass that are positively charged. Okay? Is there a question there?
If that area is positively charged, and you shoot a positive particle, why would not that go up?
So it shouldn't bounce because there's no mass. It could deflect, okay? And the deflection is a possibility, okay? But for the most part, it should go straight through because it's not impacting any mass, okay? So it could deflect a little bit, but there's nothing to cause it to really bounce. Does that make sense? Okay? So Rutherford needs an experiment to test this. So we need the alpha particles minimally. We need this mass, these positively charged particles. So that's what they're showing in this bottom diagram, a source of alpha particles. And it's aimed as a beam towards a material. That material is a piece of gold foil. So we make it a very thin piece of foil because if it's a thin piece, we increase the odds that it could possibly pass through. Okay? So, and we could see that if you take gold foil, that's what they put on astronauts, like face shields, because they can still see through it, but UV rays don't make it through. Okay? So we can get things to pass through. This big old kind of silver thing that's going all the way around is now a detector. So all that's going to do is respond when an alpha particle hits it. Right? The exact details of the response aren't important, but you could just imagine it as just lighting up. Ping, something hit it. Okay? Why is Rutherford concerned about good science and not about proving Thomson's model? If he just wants to prove Thomson's model, where's the detector? It should only be back here. Why? If Thomson's model's correct, it just goes straight through. So what should I do? Just put a detector there to say, oh, look, it went straight through. He must be right. Okay? Maybe he just wanted more funding as well. Maybe he still thought Thomson was right and wanted more money, okay, for his research project. Well, you have to prove that you need more money. So he said, well, I'm going to build a detector that goes all the way around the sample. Okay? If Thomson's model is right, should anything hit all the way around the sample? No. So that's an utter waste of material because nothing's going to hit there. So they set up the experiment, fire it up, and sure enough, most of the time they do see it pass straight through the sample and they see a little bit of deflection. Okay? All of that supports Thomson's model. But a very small percentage of the time, they actually notice detections coming backwards. That makes no sense. If Thomson's model is valid, there should be nothing bouncing. Why is it bouncing? Well, this is not correct. Good. How could we change Thomson's model to verify or explain some bouncing? What must that positively charged alpha particle be impacting? It has to be impacting something massive. And what charge does that massive thing have to be? Positive. Because if it was negative, what's going to happen? It's just going to come straight in and stick to it. Opposite charges attract. Okay, so that massive thing must have mass, and it must be positive. Okay? So Rutherford now changes Thomson's model and says, your model doesn't explain this observation. We have to have this existence of something in the middle. Okay? And middle is a relative term, but if we're just guessing at spheres, we're going to pick the middle for that, because that makes the most sense. Okay? That's the easiest way to describe it. Okay? So we pick something that is centrally located. Okay? The central unit of a family, if we had like a complete family, we might call that a nuclear family, because we have a central point. So we invented a term to describe the center of the atom, the nucleus. That nucleus is going to collect all of these positive charges. Kind of make sense? Yes?
Is that little fish symbol up there, alpha, is that what that stands for? Or?
Yes, I couldn't find the fish. Oh, there it is. Yeah, it shows them in a couple places. Yeah, alpha, that little fish symbol, that's the Greek letter for alpha. That is what we use to represent an alpha particle. If you're going to stay, if this is your only chemistry class, you're probably not going to see more than that. If you move up through general chemistry into second semester, that's typically when you discuss radioactivity, and you'll see other radioactive particles.
Wait, so it's an alpha particle?
An alpha particle is a positively charged atom, actually. What an alpha particle is the helium atom without electrons. If I take all of the electrons away from helium, I have just that nucleus. That's an alpha particle. So we were able to notice that alpha particles had mass and charge. We didn't know necessarily what built beyond them, but we knew they had mass and we knew they had charge. But we knew nothing else about them. When we learn more about them, we eventually find out that they're helium nuclei. Okay, but again, we don't have that context. We just know they're positive and massive. Okay? So, other questions about this model yet? No? You're just... Okay. So the first question that to me would come to mind is, well, where did I get these alpha particles? I have these positive, massive things. I don't even know what an atom is, or what makes up the proper composition of an atom and how it's put together, and yet somehow I have this new thing, alpha particles. Well, what the heck are alpha particles? Alpha particles were this weird thing, a phenomenon, that we saw from particular elements. Those particular elements happen to be radioactive. So certain things, materials, would eject these high energy things, and we could classify what those things were based off of some of our secondary observations. Okay? Alpha particles happen to be one of those things that could get ejected. And the biggest issue there is that could get ejected. These samples that emitted this energy usually emitted a bunch of different things. Well, that becomes problematic for Rutherford's experiment, because the whole point of this experiment is that alpha particles hit this. What if it's something other than an alpha particle? That could change the results. Maybe something's bouncing because it's not an alpha particle. Okay? So I have to make sure that the source of alpha particles can only be emitting alpha particles. That means whatever this thing is in that lead box has to be pure. I have to control that variable to make sure that the rest of the science is valid. I have to know that that is true. That becomes a challenging system because these materials that are emitting these energy forms aren't pure, and we're getting a variety of different things coming out of it. So for Rutherford's experiment to actually continue, we have to have a pure sample. We don't have a pure sample. Just like for Thomson, to get Thomson's experiment to work, we had to have a vacuum. For Rutherford's experiment, we have to have a pure sample. Yes?
Is that why you mentioned earlier that sometimes particles bounce backwards? Is that why? Because sometimes the elements he was using weren't pure?
Nope.
Or?
The sometimes elements bounce backwards is because Thomson's model is invalid and we have a nucleus. Okay? We can only make that statement assuming this is a pure sample. If it's not pure, maybe there's another reason for them to bounce. Because we've got it pure, we know it's because there's a nucleus. Okay? So in Rutherford's experiment, we've eliminated that variable. But that relies that we have a pure sample. Okay? A pure sample of radioactive material. Who might be looking to? Marie Curie. Okay? She was the one that was able to purify these elements to get these radioactive samples. Once they are purified, now Rutherford can use that pure sample to run this experiment. Without it being pure, we don't know why it's bouncing. There could be other reasons to explain it. Because it is pure, it's good. That's where Curie comes in. Curie comes in and supplies that purified sample. Okay, this is a pretty massive technological advancement. What did Curie do with that information? If we compare that out to kind of today's society, you wake up, you spend the rest of the day playing around in the lab, ooh, you accidentally discovered the cure to all cancer. What do you do?
Don't tell the pharmacist because they'll lose a bunch of money.
Okay, so we get a bunch of different explanations, and depending on kind of potentially your perspective in life, you're going to get slightly different responses. The two big responses that come out are give it to everybody. Why? Cures cancer. That's nice. Or find a patent attorney so you can lock down a patent on it and you can then sell it. Okay? I used to say the selling one was you're a horrible person. That's not true. You're not a horrible person. And this is where science and patent law kind of comes into play. Science is about improving society, or one of the aspects is making things better. So we could just make that freely accessible. If that's now freely accessible, you are a scientist and your sole reason for living is to make everybody else's life better. What happens to your life? Stays the same or potentially miserably falls through the floor. Okay? Because you're now investing time and money and effort to make everybody else's life better, but not getting any reward for it. That's why patents come into play. Okay? Patents allow scientists to get some of that, recoup some of those costs they put in. The question is at what cost? Okay? And so we've got a lot of kind of business-minded folks that say, I need that recouping. That makes sense. What is a fair price? Okay? What is a fair price for curing all the world's cancer issues? Okay? With Curie, she made it freely accessible, okay? Which means everybody had access to the technology, and not only that, everybody had access to pure samples because she distributed the pure samples. Okay? That allows Rutherford to run his experiment, get reliable results. Phenomenal, fantastic. Okay? Curie, for those of you that did research, originated where? Poland, then went to France to do all of her studying. Okay? Every nation usually has a group of scientists that all get together and say, you're a pretty cool scientist. You're a pretty cool scientist. Let's all get together so we can create a cool scientist club. Okay? They usually sell it a little bit better than that, but that's pretty much what it is. Okay? Usually it's called the National Academy of Sciences or something like that. Okay? France has one. Curie just helped Rutherford discover the atom. What does France say to Curie? No women allowed. Can't join our club. Okay? Remember, this is early 1900s. Women don't have a right to vote. Okay? Women pretty much have a right to, well, nothing. Okay?
Don't be seen, don't be heard.
Okay? And yet she's making these massive contributions and she's getting ignored for them. Okay? At least within France. Because if we take a step further back, she does get a Nobel Prize for this discovery. Okay? What else does she continue to do? She keeps working on radioactive materials and gets another Nobel Prize. Okay, so she's the first person to obtain 2 Nobel Prizes. Okay, what's extra cool about that, okay, is it's 2 Nobel Prizes in not only 2 different fields, but 2 different science fields. I believe there's only one other person to have obtained 2 Nobel Prizes. Also a chemist. That's why you should stay in chemistry. You increase the odds of becoming a Nobel Prize winner. Okay? Linus Pauling gets it for chemistry and for peace. So Curie, a woman, existing in a time where they're not allowed to be seen, heard, or whatever other adjectives you threw in there, okay, creates a massive leap forward for science in a system where she wasn't allowed to be heard. This is probably the largest argument that science needs to be more inclusive, not less. Okay? So think about that when you move forward and people try and chase you out of things. You can probably contribute to that area. Yes?
Wasn't it true that she wasn't even going to get the reward and was just going to go to her husband and the partner that were on it, and then they got like a letter from Albert Einstein or something like that? Or was that the second award?
I don't know the details behind that. I would not be surprised. But yeah, I don't know enough details on her history. Arguably, everybody studying Curie right now should be doing a lot better job than I am. Okay, so that's kind of cool. Okay, I think that's a neat little history. To that, after that, we got the alpha particles, we get Rutherford, okay, which then means we get a nucleus. Okay, what's in that nucleus? All the protons. Okay, well, why did Thomson not say, well, all the protons should be in one place?
Is it because of the angle it's reflected?
Thomson didn't have this experiment,
Oh.
remember? So why did Thomson not come up with the experiment that all the protons are in one location, but instead scattered? We have protons, we have electrons. These are roughly equivalent to the north and south ends of a magnet. What happens when I take 2 north ends of a magnet and bring them near each other? They repel. So Thomson's mind, I have a positive and a negative end. Does it make sense to take all of the positive things and put them in the same spot? No, because what are they going to do? Repel away. So that's a horrible theory. Rutherford just goes through and says, sorry, your idea of a horrible theory, not so horrible. All the positive charge is located in one space. Okay? That's a little bit bizarre. So what might Rutherford suggest also has to be there? We could try and do electrons. Unfortunately, the electrons are what's making up the size of the atom, so that doesn't quite work. Something has to be there to hold those protons together. Okay? Whatever that thing is, doesn't have charge. And our term for no charge? Neutral. Hence the existence of neutrons. Okay? Rutherford doesn't have evidence or doesn't know a neutron exists. He just postulates that it must exist because I know all the positive charges in one spot. Because all the protons are in one spot. Kind of make sense? Okay. To deciding about the electrons, we get an idea of the size of the atom. Okay. This can be a bit confusing for people to process. You can see numbers like this. An atom is about 10 to the minus 8 centimeters. A nucleus is 10 to the minus 13 centimeters. Okay. We've got a couple big problems with this. Powers of 10, which nobody likes, and negative symbols, which nobody likes. Okay, so we can't really wrap our human brains around those numbers. And really all we end up seeing when we do those comparisons is that the diameter of the atom is, for those of you saying, well, that's totally not true, this is totally how we as humans envision this. Well, what's the big deal? Okay, because we can't deal with those powers of 10. Our brain is puny and small, it can't deal with that. Okay? This is why when we talk about the national debt, we talk about it in trillions. Because if you go trillions, well, that's not that big a deal. It's just, what are we at? 22?
Almost
22? 23? So let's just say 22. 22 trillion. You're like, 22, that's not that bad. You know, I got 20 bucks in my wallet. I can just pay that off. That's not a big deal. We don't go 22 0.00000000000 because that's too hard for our brain to process. So we invent a word to replace all of those so that we can sort of wrap our head around it. Right? Unfortunately, we've lost a lot of meaning. The same thing is happening with these powers of 10. So let's scale this. Let's make the atom the size of the Superdome. So any stadium you want to envision, okay, unless it's made for ants, not that one. Any stadium, take a marble, that's your nucleus. A marble inside the stadium. That's how compact the nucleus is. Okay? So we're really dumping those positive charges on top of each other, which means we're going to have something to hold them there. That's why we get the idea of a neutron. Neutrons were later experimentally discovered by Chadwick. Okay? It's about the same size as a proton, but it doesn't have charge. Pretty much its sole purpose is to keep the protons together. Okay? To give you an idea of kind of nuclear dimensions, let's just say a proton is a marble. Okay? If I take a look at hydrogen, there's only one proton. So do I need any glue? No. So there's no neutrons typically for hydrogen. Okay? But if I move up to helium, what happens? There's two protons. Well, what are they going to try and do? Repel. So what do I need? I need some glue to hold them together. There's the neutrons. As I continue to add protons, what am I going to have to keep adding? Neutrons, or more and more glue. Okay? As we try and glue our marbles together, eventually what happens? Remember, these all have to happen at the same time. Okay? I'm building a nucleus. Eventually I add so much glue that the glue stops holding the marbles in, which means what happens to our nucleus? It starts to fall apart. What is that falling apart? Radioactive decay. Okay? There's now so much crap in there that it literally can't hold itself together and it starts to fall apart. Okay? If we were looking at the analogy with the marbles and the glue, it just kind of melts in a big nasty mess. When we're looking at atomic structure, it falls apart in very predictable fashions. Okay? That very predictable fashion is an alpha particle, for example. Okay? So, back to everything. We talked about a bunch of scientists, all their fun discoveries, and they come together with our subatomic particles and get us all of this information in this nice little table. You need to have this memorized, every little piece of this. Okay? They're saying, well, it's not bad to memorize it. The memorization isn't the problem. It's the application of this out that's going to become a problem. So when we move further on, I'm going to be asking, how do we determine this? How do we determine this? It's going to be an application of these rules. Okay? We look at the electron. That's a bunch of letters. What do we do? What do we do with a bunch of letters? We shorten it. Okay? And we write just a single letter to represent it. Because we are speaking English, those are the letters that we picked, right? And we've got that. What's found in the upper right-hand corner? The charge. So it's a simple way to notate the information in one kind of central location. So we get the charge and the symbol for each of those. The next part, you need to know something about locations. Electrons are outside, protons and neutrons all mashed up on the inside. If I ask you about the size of the atom, which of those particles is going to contribute to the size of the atom? The size of the atom. So if I asked you to describe my size, what might you use to describe my size? Okay. My size. I don't care about protons, neutrons.
Centimeter?
Describe my size. Okay, I got a tall.
Your weight.
Short.
My weight. Okay. And thank you for being tall. I've used you as an example of, am I tall? And everyone goes, yes. And I go, no, I'm short. Gabe's taller than me. Okay. So we could use height. We could use weight. That becomes challenging. Size is a vague term to use. The language is inappropriate. If I ask size, when we're talking about atoms, I'm talking about the height. Okay? Or in this case, how round the atom is. Which particle contributes to the quote-unquote height of an atom? The electrons. And only the electrons. If I'm now concerned about the mass of the atom, which particles contribute to the mass? Don't electrons have a mass? So electrons do contribute to the mass. How important is that mass? Not very. Okay, to give you kind of an idea here, 1 over 1,836, my hair, a single hair off my head, is probably close to that mass in comparison to my body. Okay, so if I want to lose weight, because I've decided I'm overweight, I'm going to step on the balance, I'm going to get a weight, I'm going to step off the balance, I'm going to lose some weight today, and I step on the balance. Am I going to be happy with the result? Why not?
You're going to be bald by the end of the day.
Could very well be bald by the end of the day. And even then, am I going to see much of a change? No, because the relative comparison of my hair to the total mass isn't a big deal. Same thing's happening with our electron. It doesn't contribute that much to our mass, which means a better number to memorize for the relative mass would be what would be a better number to memorize for the mass of an electron? 0. It doesn't contribute to the overall mass of the particle. It's not true, but as a pretty good blanket approximation, that works well. Make sense? Is that a yes?
Sure.
Sure. Damn it. Yes.
It goes to a test, and you're asked basically for the electron mass, you want to put none, like you
Yes.
zero, none.
Yep.
Okay.
So if I asked you for the electron mass, I fully expect you to write
none.
0.
Oh, 0 and none is different, so you know what I mean?
Yes.
So either one goes.
Yes.
Okay, awesome. Just to clarify.
Yeah. Where would I ask that? So remember, on the chemistry exams, there's 2 places that you can get questions. You can get show your work, or you can get multiple choice. Where would I ask you about the mass of an electron? Okay, why would I ask it in a multiple choice, not a show your work? It just is what it is. In a show your work, what's the work that you're showing me to tell me that it's 0? There's no work for me to grade. Okay? I could ask you to try and do some explanation of why it's 0, but then I've told you it's 0. Okay, does that make sense? So that question on tying back to 0 is a multiple choice question. It's a fact, not an application.
So, I don't know if you know this, but so on the Rutherford model, they use radium-226, right?
I believe so.
Instead, since it was discovered after uranium, why didn't they just use uranium since it's more pure?
Uranium wasn't pure.
It was not at the time.
Yeah,
So radium was more.
yeah. I think that was the issue. Yeah. And the exact details on which samples I'm not positive on, but at that point, some of it isn't just that it's radioactive, it's how is it radioactive. It has to be emitting an alpha particle. So every radiation doesn't necessarily emit an alpha particle. It could emit an alpha particle and a beta particle. It could emit a beta particle. Or it can do gamma radiation. So you can get a variety of different sources. So we have to be careful that the radioactive source we're picking gives us alpha particles. Okay. And that the very next piece of it doesn't do something else. Okay. So now we get to, because I covered this in the standalone, and they're like, why did you talk about all this? Because by the end of it, I pretty much deleted the entire slide. So let's start off with why we talk about this. You are responsible for it. Okay? You are responsible for the term atomic notation and that symbology down at the bottom. Okay? So what we are going to address when we go through and talk about this is what all of that means and ultimately why it's a bit obnoxious to make you memorize it. Okay? So let's start this off. What makes an atom? The pause there was a little bit disconcerting, right? Okay. Protons, neutrons, electrons. Okay. So we're talking about atomic notation. All this information on here, and of course, yeah, I'm irritating like that. It's okay. Do you see the word protons? Awesome. Do you see the word neutrons? Yes. Do you see the word electrons? Isn't the atomic notation referencing everything that would make up an atom? Yes. Why are electrons not specified in the atomic notation? Because it's not effing an atomic notation. What is it? If we're only representing the protons and neutrons within this, what are we looking at? We're only looking at the nucleus. This isn't really an atomic notation. This is better known as well, we could call it a nucleus notation, but due to the English language and all that, we have to conjugate that verb around, turn it into an adjective. And we get nuclear notation, because all we're concerned about is what's happening in the nucleus, at least within how this has been expressed. Okay, and we'll make some modifications to it as we go. Okay? Who might be concerned about the nucleus? Potentially combining other things. Like if I react two atoms with each other, am I concerned about their nucleus? It's kind of a hard question because we're really early in the chemistry class. What's the most likely thing for two atoms to see when they interact with each other? The electrons. Do I care about the nucleus? No. Nope. So I don't agree necessarily that two atoms is going to be concerned about a nucleus. Who's going to be concerned about nuclear notation? You. Why would you be concerned about nuclear notation?
Students have to know it for a test.
Sort of fair, but not quite. Do you think Chadwick was concerned about it? Why was Chadwick concerned about it? People that studied Chadwick. What was one of the things that he contributed to? The atomic bomb. Who's concerned about nuclear notation? People working with nuclear radioactivity, atomic bombs. Right? So what we're talking about is the elements that would be radioactive. Based off of your current knowledge, what elements are you going to be like, that's radioactive? Uranium. Where is that? The hint at U. 92, it's at the bottom of the periodic table. Okay? There was a suggestion about radium. Radium is Ra. Where is it found on the periodic table?
88.
88, bottom of the periodic table. Polonium, radioactive, bottom of the periodic table. Where are a lot of our radioactive elements? The bottom of the periodic table. What is different about elements at the bottom of the periodic table in comparison to the top of the periodic table?
Yeah, more protons.
Their nuclear size has changed. Elements at the top have relatively few protons. Elements at the bottom have a lot of protons. The more protons we have, the more neutrons we have. We're adding more glue. The more glue we add in there, eventually what happens? It starts falling apart. Our radioactive elements are all at the bottom of the periodic table. And it's really a balance of the glue to the protons, the neutrons to the protons, that's important. So as a nuclear chemist or a nuclear physicist, I'm going to be concerned about what makes up the nucleus. So if I'm going to invent a notation to describe what I'm working with, what is the very first thing I want to see? The protons and the neutrons. Because we are an American-based system or an English-based system, we read left to right, top to bottom. Where should I place that very important information? Top left. So in the top left of my nuclear or atomic notation, I write the sum of the protons and the neutrons. Okay? Because we don't like mathematics symbols, we don't write sum of protons and neutrons. We invent a word to describe what that means, and we have the mass number. So your mass number is written in the upper right because of the importance of the nuclear notation. The larger that number is, the more likely it is radioactive. Now I'm more concerned about it as a nuclear radioactive system.
I'm trying to remember. I'm sorry.
You're good.
I'm trying to remember from my old chemistry class. Is it the mass number is like protons and neutrons, or not neutrons, electrons? They always have like the same amount, right? They have to.
So I'm going to have you hold on that concept of electrons because they aren't here yet. So until we explicitly bring in the electrons, I don't want to talk about them. Okay? But they are important and they are factored into this, just not obviously yet. Okay? So at this point, we have the mass number in the upper right-hand corner. That tells us big number, whoop, that's radioactive. Well, I can make a bomb out of it. That's slightly overstated. Okay?
I like it.
After that, what other information might I want to include? Okay, I could include the number of protons. Okay, where might I place the number of protons? Right below it. Why would I place the number of protons immediately under the number of protons and neutrons? How would I figure out the number of neutrons? Subtract. So if I write the big number on top and the small number underneath and I go minus sign, that looks an awful lot like the standard long subtraction method for being able to write out the number of neutrons. So I can determine that relatively quickly with that organization.
So why don't they just write the number of protons and the number of neutrons?
Why not just split it? Because it's the balance of those two that becomes important. And yeah, we could reference that, but again, it's the size of those that really contributes.
So if we tie that back to some of the things we talked about with like the context of writing, these scientists are drawing in common mathematical ways of structuring to make it easier to process the science. Does that make sense? They're using this genre of writing that's a mathematical notation and building into what is they're taking this common form of mathematical notation, building it into the science, and building off of that genre.
To create a new one, right?
And to better understand the chemistry, to contextualize that genre in this new situation, in this new environment.
And to that same extent, we're looking at a visual design. How do we organize this? Okay, some of that visual design is overlap from the other genre. Okay, but we're using that to kind of embed that information so it becomes more kind of second nature. Okay? So we could just list the mass number and the atomic number and be done there. But are we done? No, what else do we add? We write, do you see the number of electrons yet? I know everybody's just jumping all over electrons. Look at what you've got. We provide the symbol right next to it. So we've now got all of this kind of information into one neat, tight little package, and we've got our nuclear notation. Okay? We don't want to write out the full name because we're lazy, but if we wanted to take advantage of this, we could say write out the information. So for instance, we could go through and write out radium, and then dash. What would be the important information if I was going to write this out that I would now want to include after this dash?
Mass number.
Why the mass number?
The higher the mass number is, more it's radioactive.
How many protons does radium have? Well, I didn't write it down. How would I possibly know that? And I saw a lot of people like shifting their view, which was fantastic, which is intentionally why I threw in that statement of like why I didn't write it down. How would I know?
I actually have a question, because this is where I get a little confused, because radium-226 is lead-212 and carbon-14. So that's what
Talk to me after class.
Okay.
I think Allie has an actual answer to your question.
What's your... Yeah. We looked at the periodic table. Okay. I want to know how many protons radium has. So what's the first thing that I would need to know to figure that out on the periodic table?
Its abbreviation.
I would need to know that radium is Ra. Once I know radium is Ra, what can I do? Find it on the periodic table. There are two numbers associated with it. Okay. What are those numbers? Well, this one's above, so that must be the mass number, right? Why not? Okay, good. It's smaller. I like that. That's good logic. Keep going. There's an easier answer.
To the right.
It's on top.
Mass number is on top. To the right, that's an interesting pass on it. That would kind of work. And no one, I don't think I've seen a periodic table that puts it in the upper left, which would be a good thing. But I would say there's another answer to explain why that is not the mass number or the atomic number.
because it's in like 1 to 118 or whatever.
Okay, you're in a writing class, right? You're given a text that you're like, I don't know how to interpret this. What would you start to try and do to figure things out? Okay, you could look at order or structure. You could look for maybe like a glossary of terms on where to find things. Because this is a picture,
Oh my God.
holy cow, there's a key that tells me the number in the upper right-hand corner is the atomic number. Because I know the atomic number is the number of protons, there it is. Okay? Use the information given to you. You're given a key to tell you that the number in the upper right-hand corner is not the mass number. You're told it's the atomic number straight off the key. That's why we know that's the number of protons. Okay? So when I write radium here, just the action of writing out the word radium, I now know the number of protons. It's 88. Should I write 88 here? No, that's not new information. Which brings up an interesting point about back there, which we'll get to. So what would be new information we could write here?
Mass number.
The mass number. Okay? So I could write 226, because that's what this periodic table seems to suggest. Is that number underneath each of these elements the mass number? No. How do you know that? Because if we look at our key, it does not say mass number. Phenomenal. There's another reason that's harder. If it was a mass number, what would that number always be?
Whole number.
A whole number. And when we look at all of the atomic weights on the periodic table, are they all whole numbers?
No.
No. Why? Because they aren't mass numbers. Okay? So, by writing radium-226, I'm now identifying the mass of that particular atom. I've also specified its atomic number. Okay, so those are two kind of critical pieces of information. So if we go back to this, do I really need to write the atomic number? If I tell you Ra here, what is the atomic number? 88. How do you know that? It's on the periodic table. When are you going to have a periodic table? Always, because
Because you're awesome.
You are chemists. So by corollary, you are also awesome. Okay, chemists always have a periodic table on them. Yes, I do. Okay, I used to actually have a hard copy, but technology, we always carry a periodic table. We can look that number up. For the sake of the class, it's on the board. It's also the second page of your exam. You will always have that information, which begs the question, why is it written in for the atomic notation? I completely agree. I think there's a pretty solid argument that we shouldn't even need to include that. Are you required to know it's there? Yes. It sucks for you. And me, because I have to present this to you in a way that you're like, yes, I want to memorize this. Okay? I have to write it as atomic notation because that's how it's presented. Okay, so that's why we've addressed both of those topics and why it doesn't outright say nuclear notation at the very beginning.
So the mass
I know.
number is the one on the left, that's the atomic weight.
The mass number in atomic or nuclear notation is written in the upper left-hand corner. On the periodic table, it's not written there. Why might we change where information is located? What is the rhetorical value for changing where I would put information?
Could be like a sociocultural thing.
We could get to sociocultural, and ultimately it's going to be a sociocultural norm within the field of chemistry. I'm an organic chemist. As an organic chemist, what elements do I deal with?
Not, what is it, like non?
You're right. What's in plants? What's our element that we're looking at?
Carbon.
Carbon. Where's carbon on the periodic table?
Number 6?
Top of the periodic table. Do I care about the radioactivity?
No.
No. Do I care about the mass number? Am I dealing with radioactivity? No. The mass number is all about nuclear reactivity. I don't care about the nuclear reactivity because the element I'm working with isn't typically radioactive. So when I change to a different area of focus, I'm going to decide this symbology is going to have different meaning for me, and I'm going to want to change how I represent it. When we go to the periodic table, what are they trying to represent by putting the atomic number on top and not the mass number? How do you read? Left to right, top to bottom. So we start with hydrogen. What's the number? 1. Left to right. 2, which would be helium. If we had the mass number up there, what would it be? 1. If we had the mass number. 4. I don't know how you count, but I don't count 1, 4. Okay? So we've swapped the organization of it on the periodic table because I'm trying to draw attention to a different piece of information. I'm trying to draw attention to the organization of the periodic table based off of atomic number, not the mass number. Why? Because the atomic number allows me to get different connections. Why does a nuclear physicist care about the mass number? Because that's going to explode on me. That's why I want to see that information first. So we change how we represent that information based off the field that we're in. You're pacing a little bit. Did you want to add?
Yeah. So again, that is a rhetorical consideration that scientists go through on an everyday basis as they consider this stuff. They're thinking how they structure the information is based on that rhetorical idea of what is my right or purpose. If my right or purpose is to know this thing because I'm a organic chemist, that's a direct writerly consideration that scientists or chemists have to be aware of.
Make sense?
And it helps
Writing
them
in
read
chemistry?
the key documents in the field.
Okay. So, mass number, we just said, for me, what the F? I don't want to look at that. So, we could make the argument that me as a chemist goes to this. All I care about is the symbol? If I bring two atoms near each other, what's the first thing that interacts? The electrons. Okay, because they're on the outside. Remember, they made up the volume of it. Guessing and being wrong is a phenomenal thing. Keep doing it. Okay? So our electrons are concerned. Where in that notation do we see anything about electrons? We don't. Okay? That's because the textbook did a poor job drawing attention to it. It's actually embedded in there. We just haven't written it in. Okay? Remember, we had some information stored at the upper left and lower left of this symbol. Okay? Which really means what we've got is kind of a box around this. Is there another space where I could put information? We could go on top of it. We could go below it. And we also have behind. I see what you're saying. To the right of it, yes. Oh, it's like, I can't write behind that. Yeah. To the right, yeah. Right, up, and down. Yeah. Okay. Sorry, organic chemists I see three-dimensionally. So when you say behind, I'm referencing a different direction. Okay. So we could write information over here. Have we seen information written on either end of that? No? Really? What was the formula for water? You want to tell me you haven't seen information stored to the right of a symbol? Again?
No.
No. Why not? Is this 2 applying to the oxygen? No. Because if that 2 was applying to the oxygen, that would be saying it was the atomic number, the number of protons. Does oxygen have 2 protons? No. So it can't possibly be referring to the oxygen. What is it referring to? The hydrogen. What about the hydrogen is it referring to? It has. What does that 2 mean?
2 hydrogens.
2 hydrogens. The lower right-hand corner tells us the amount of that individual element in that compound. We have that information. Okay? That is an important thing to note, and believe it or not, you will probably screw that up at some point during the semester. Okay, but there it is. Which means we're missing a spot. There's a hole where we could place some information. The top right. What do we put in that top right corner? If it was the electrons, why was it not explicitly written in to begin with? Okay, it's not just the number of electrons. It's going to be the charge. What is going to dictate the charge? The balance of the protons and electrons with each other. And because protons are positive and electrons are negative, when we add their respective total charges together, we get the overall charge. So the overall charge comes from the balance of our protons and our electrons. And we could memorize it as a system of protons minus electrons. I would argue it's really the charge on protons times the number of them plus the charge on an electron, which is -1 times the number of electrons. Because I know those charges, I don't have to remember a formula because all I'm doing is just adding them up. Make sense? This is, again, applying that information. So charge is embedded in there. Why did they not show it initially in this notation? What was the assumed charge? Neutral. There was no charge. If there's no charge, what would be the mathematical symbol for it? 0. We're dropping the 0 when referencing charges. Okay? So altogether, when we're looking at our symbology within chemistry, we have all of these pieces. Okay? Your atomic notation or nuclear notation is officially that. Recognize that the upper right and lower right also hold information about charge, which gets us our electrons, and the amount of that individual element. Kind of make sense? Okay. This is why students were like, well, what the hell? Okay, you just showed me all this stuff, and then you deleted it all and just said the stuff that wasn't there was important. Yeah, I did. Okay? So, you ready to apply it? No. Yeah, I appreciate the confidence. It's good. What is the element? How do you know the element is silicon? What are you memorizing to say that it's silicon? Yes? The letter code SI means silicon. What if I'd hidden the SI? How would you know it was silicon? You'd look at the atomic number, which would be the 14, this number of protons, and we go to 14, we find Si, which we know to be silicon. Okay? So our atomic number is 14, which happens to be the number of protons. Okay? We know the mass number is 29, which means the atom of silicon has, which is kind of a stupid question because it's really the bottom question. The number of neutrons would be 15. How'd you do that?
29 minus 14.
Right, 29 minus 14, and we get 15. Make sense? Okay. To kind of throw this out there to give you an idea of how this can become kind of a confusing question on a multiple choice, is I could say, what is the number of protons for silicon? Okay? And you'd be like, well, that wasn't that hard of a question. We're staring at the answer, so work with me a little bit. Answer choices. 14. That's good. That was the answer choice. That's the correct one. That should be one of the answer choices. 15. Okay. What is the interesting bit of information about all three of those?
They're all part of the.
All three of those are embedded in that given information in some form or another. If you don't know specifically what information tells you the number of protons, every one of those becomes a potentially valid answer. This is a common theme with every single one of my tests. You would not get three answer choices like this. 14, 2, 23. What does 2 have to do with any of this? Nothing, which means you could immediately eliminate it as a nonsensical answer. You could do the same thing with the 23. Okay? Test questions are written so that all possible answer choices have some grounding in the given information. You have to apply that given information correctly. Does that make sense? Okay. Welcome to my class. Whoa, come back here. So, because we've already talked about it, you guys should be able to go through and do this really quickly. So let's take a swing at it. Way to just jump straight in, outside. I'm going to guess that's what you were referencing, the very first one. I like it. What do we got next? So I guess we're going down, right? Inside's a bit vague. I don't quite accept that one, actually.
Nucleus.
That says nucleus, and that just says nucleus. What else you got for me? 0. Charge.
1, and 0.
What is the charge on an electron?
Negative.
Negative 1, okay.
Positive 1.
E with 2 minus E with
Good. E negative. And it's N technically 0. That 0 almost never gets dropped because we're really trying to force that on neutron. Okay, to emphasize that. So notice again what was written in the upper right-hand corner. The charge. It was the balance of protons and electrons. For a single electron, how many protons are there?
1.
For a single electron, how many protons are there? 0. There's only an electron. For a hydrogen atom, how many electrons are there? 1. How many protons? For a hydrogen atom? 1. Because the atomic number is 1. What would the charge be for a hydrogen atom? 1 proton, 1 electron. 0, because the electron charge is a negative 1. Those charges cancel.
Bless you.
Kind of got it? Here's the fun one, meaning. What does an electron mean? Okay? If it means negative charge, I'm going to argue that I already said that, so no. I like where you're going with that, though. Okay? So I would argue our meanings become easier if we start with protons.
I only know this because I'm taking the class, but it's if the proton defines the element.
If I say 2 protons, what do I have?
Helium.
If I say 27 protons,
Cobalt.
cobalt. Okay. Cobalt's a common one because of copper and carbon, so that's one of the ones that you should go back and try and memorize. Okay. So the protons define the element. Once I've defined the element as carbon, what are the number of neutrons? Or let's go to electrons. What do the electrons contribute? For carbon specifically. I didn't say how many electrons, I just said what do the number of electrons specify. So I say carbon, let's add to it, let's make it a less ambiguous question. Carbon, 4 electrons. If I have 4 electrons on carbon, carbon has 6 protons. Because I know it's carbon, I know it has 6 protons, because that defines the element. With 4 electrons, I now know the balance of the charges, and I know the overall charge for that particular carbon is going to be a positive 2. So electrons will define charge. Yes, protons contribute to it. This is why we started with protons as our definition. Once we've established what our proton is, we have the element. Now to define the charge, I have to know how many electrons contributed to it. All right?
Bless you.
What do neutrons define?
The weight.
Officially, mass, weight is allegedly gravity dependent. I use them interchangeably. Physicists can yell at me later. Okay? Because protons, if I say carbon and 6 neutrons, you can now tell me the mass of that atom. You can't tell me anything about the charge because I haven't told you anything about the electrons. Okay? But if I tell you carbon, 6 neutrons, you can tell me it's carbon 12. Because 6 and 6 is 12. That's the mass number. It defines the mass. Kind of, sort of? Okay. So, when we go through and deal with naming, we're going to be looking a lot at defining the charge. When we look at isotopes, we're going to be looking at defining the mass. Okay? And because I kind of want to do that instead of a quiz, what we'll go ahead and do is, I think, skip through the quiz. Not a bad idea to go through and look at that quiz for your own reference to make sure you understand some of the information there, because that stuff is stuff that I think is not only important enough for me to have presented in class, but then to also have asked about in class. Okay? Isotopes. Okay? Protons define the element. Neutrons define the mass. Mass isn't sciencey enough, so we invented a new term. That term is isotope. Okay? Iso for same, tope for element. No idea. I just made that up. Oh, there we go. Same type. There we go. So same type. Okay? But it can't be the same thing because then I would invent a new term for it. Okay? What we're referencing is the same type, but something is different about it. What is that different? The mass. If I take a look at hydrogen, I can reference hydrogen with 1 proton. How many neutrons? 0. You're like, damn, but there's a 1 there. What is that mass number? Protons and neutrons. If there's 1 proton and the mass number is 1, how many neutrons must be there? 0. Okay? So I can define that particular thing as protium. Okay? Why would I call it protium? What's in the nucleus? A proton. Proton. It's in the name. What happens if I happen to discover, and it does exist, a hydrogen nucleus with a neutron in it? What happens to the mass? It changes to what? 2. 1 proton, 1 neutron gets me a mass number of 2. There it is. I want to come up with a name to reference this. Okay? I could call it proteutium. That actually sounds kind of cool. But no, we didn't pick that. What did we pick? Deuterium. Deuce for 2, referencing the number of particles in the nucleus. Okay? So we get 2 different isotopes. Why are these isotopes come up with different names? They're commonly enough studied that we created a new name. Almost all elements have the potential to have isotopes out there. Not all isotopes are stable. So when we're thinking about isotopes, we really only name the ones that are commonly used, studied, right, and found in existence. That's why we wear safety goggles. Right? You have me as a teacher. Make sense? Okay. How does this contribute to the information we find on the periodic table? Well, the periodic table doesn't say mass, it says weight, and it says atomic weight. We could also call it atomic mass, not mass number. What is the relationship between the atomic mass and the mass number? That is a mind-boggling question that it looks like you are all super excited to discover on Tuesday.